Hello, welcome to this joint webinar by Ahlstrom and Ethos Biosciences. My name is Ryan West. I'm a project manager for development at Ethos Biosciences. I'm going to be giving the first part of this webinar, and then I'm going to hand it off to my partner, Frederick Bebian, at Ahlstrom. The topic of this webinar is about design and development of lateral flow assays for not only performance, but manufacturability. And the real take home here is that when you go into development of any assay, including a lateral flow assay, you're going to be making hundreds of decisions. There are going to be 100 decision points where you're choosing materials or reagents or protocols. And those decisions will be based on what's going to give you the desired performance, but also what's going to lead to a smooth transition to manufacturing. And so the real gist of this talk is to think ahead to manufacturing and think about some of the issues that you may encounter early on in the development process so that design transfer is smooth. So we can start with what is a lateral flow assay. It's an immunoassay for quick, simple, and inexpensive detection of a target analyte in a sample. Results can usually be had within 5 to 30 minutes. You can detect a wide range of analytes that include proteins and small molecules, but also nucleic acids and other things. Minimal or no equipment requirements. They're cost-effective, handheld, and all of these attributes really lead to them being extremely effective for point-of-care and at-home testing, and also ideal for measurements in the field or low-resource settings. So how does a lateral flow assay work? So there's different configurations of lateral flow assays, but they all share some common design elements. And so here at the top of this slide, we see the basic components of a lateral flow assay. Again, these are going to be shared by many or most lateral flow assays. First, there's a laminate card or a backing card, just a solid card upon which other materials are adhered. And then on top of that, a number of materials. The first one is the sample pad. The sample pad is where the sample is introduced, and from there, the sample wicks through capillary action across the pad, in this image from left to right. The sample pad overlaps with a conjugate pad, and upon this conjugate pad is a dried conjugate, such as a nanoparticle with a bioreceptor on its surface. As the sample pad flows across the conjugate releases from the pad and flows with the sample onto the nitrocellulose membrane. As these components flow, the nanoparticle bioreceptor conjugate has an opportunity to bind to any target analyte in the sample. Across the membrane are two dried reagents. The first makes up the test line, and that's a capture antibody or other bioreceptor that will specifically capture the analyte. As the sample flows across that test line, any analyte present will be captured at that test line. Along with it will be the nanoparticle indicator. And so as those nanoparticles concentrate across that line, you can visualize the line, and that tells you, in this case, the presence of your analyte. The second line dried across this membrane is the control line. That also has a bioreceptor, but in this case, it's specific for binding to the other bioreceptor on the nanoparticle. And so any unreacted nanoparticle conjugate that reaches the control line will be localized on that line. And so you'll have both lines light up in the presence of the analyte. The type of lateral flow that I've outlined here is known as a sandwich immunoassay. So we get both lines turning, in this case, red in the presence of the analyte, and only the control line red for a negative sample. There's also another type of immunoassay known as a competitive assay where the opposite trend is true. So the control line only lights up in the presence of a positive sample, but with a negative sample, both lines turn red. So now we want to talk a little bit about the pathway from development of a lateral flow assay to manufacturing. And of course, the first step in any development is to identify the need for the test. And here we see a number of different areas of application for lateral flow assays. Of course, medical diagnostics and animal health, agriculture, food safety, environmental monitoring, forensics, and many, many more. And so during this stage, you'll begin to identify why you're developing the assay and what exactly it's going to detect. Then you enter the design and development phase. And here you'll really start to pin down what your design inputs are. So what particular analyte are you going to be measuring? What's the required sensitivity, specificity, dynamic range, and a host of other attributes or properties that should be met once the assay is developed. During this phase, this is where all of these decisions need to be made. Decisions about material selection, that includes the type of membrane, the conjugate pad, sample pad, and wick pad. The selection of your label, will it be a gold nanoparticle or something else, and how you're going to conjugate your bioreceptor to that particle. Selection of capture and detection reagents, and the format of the assay itself. Is it a sandwich assay or a competitive assay? Will it be housed in a plastic housing or a cassette, or will it be a simple dipstick test? And will the test need to be quantitative or can it be qualitative? So during this design and development phase, all of these things will be tried out and optimized and eventually verified. And really what this webinar is really focused on is to give you some ideas during these different decision points, not just about how to meet your performance criteria, but also how to enable a good design transfer to manufacturing. And then we reach the design transfer phase, where we're going to take this developed design and transfer it up and validate it for manufacturing. Now, in an ideal situation, the design and development phase has resulted in a fully optimized and verified test. We know all the materials and reagents that need to go into the test. We've secured supplies of all these critical reagents. We've finalized the manufacturing protocols, and we've finalized the testing protocols. And in this case, you think design transfer is smooth and efficient because you're just handing off documentation to your manufacturing partners. But in reality, and what we see a lot, for instance, at Ethos here, is that a manufacturing group is actually engaged during the design and development phase. They're engaged before the design is fully developed or toward the end of that development phase. The materials may not be completely finalized or not optimized for scale up and manufacturing. The critical reagents may not be finalized, and protocols are draft only or may need to be altered. So really, we think about design transfer as a collaborative effort between the development team and the manufacturing team. So as you're developing an assay, it's important to kind of think ahead to this collaborative process, to this design transfer process. And one thing to keep in mind is that the best lateral flow that you can develop in the laboratory at small scale is not necessarily the best one for manufacturing. The reasons may be the cost of reagents or materials, which may not seem like a lot when you're doing small scale development, but can really start to add up when you scale up for manufacturing. Other reasons include availability or lack of availability of your critical reagents, scalability of your conjugation reaction, scalability of strip production and cassetting, and other kitting processes. And also, thinking about lot-to-lot reproducibility and even within lot uniformity, things that may not come up much during small batch development phase, but will become a very big issue during manufacturing. So ultimately, it's really important to develop your assay with scalability in mind. And so now we're going to go through about 4 different points, decision points, during assay development, where we can begin to take manufacturing into mind. So the first has to do with critical reagents, and in particular, the cost and availability of those reagents. So first off, what are critical reagents? These are defined here as components critical to the performance of the assay, and more importantly, components that are not easily substituted. These include antibodies, but also, say, the nanoparticle labels. So with antibodies, these are a key pillar of the performance of your assay. These will define, in many respects, the ultimate or achievable sensitivity and specificity for your assay. And the prices for these reagents can vary wildly. You can have prices that are $100 per milligram or thousands of dollars per milligram. And while during development, again, at small scale, those prices may not seem like a big difference. Once you scale up, they can be a considerable fraction of the material cost of your test. So it's important to keep that in mind early on. You also want to make sure you can get these antibodies in batch sizes that are anticipated for scale up and that they have good lot-to-lot reproducibility. As far as the nanoparticle label goes, many of the same things still apply. You want to make sure you can get your nanoparticle labels and the lot sizes needed for development, validation, and manufacturing. You want to consider cost. So we have more information there on the next slide about the nanoparticle labels. There are a number of choices when it comes to your labels. And again, your labels are what are going to give you that visual indication or some sort of indication on the nitrocellulose membrane. The most common nanoparticle label you can have is colloidal gold. Produces a strong red color, either in solution or across the nitrocellulose membrane. And that's good for both visual reading and by using an external reader or a scanner. Gold nanoparticles come in various sizes and shapes, which just allow you to tune and optimize the response of your assay. They can be functionalized with bioreceptors a number of different ways, including physical absorption and covalent binding. They're relatively stable and they're relatively inexpensive. In some cases, colloidal gold can lack the sensitivity of some alternative labels. So what are the alternative labels? These may include quantum dots, fluorescent particles, SIRS tags, that's surface enhanced Raman spectroscopy, and upconversion nanoparticles, amongst others. Many of these labels have been developed and are being used because they can result in increased sensitivity, particularly for quantitative tests, but also for qualitative tests. But of course, that comes at a price. Relatively expensive compared to colloidal gold. They often, not all the time, but often require a reader or a scanner. And the conjugation process tends to be more complex. And so here we already see the trade-off that we'll see over and over again in the next few slides. Colloidal gold here has been widely adapted, it's widely used. Conjugation strategies and optimization strategies are widely known both in development teams and manufacturing teams, and it's less expensive. But if your assay requires a different alternative nanoparticle label, it requires the increased sensitivity that those can give, then there are options. And what I'll say here is that if you need that increased sensitivity, then go for it. If you don't, keep it simple. There's also the conjugation to consider. So this is one of the more can be one of the more labor-intensive parts of developing your assay and manufacturing your assay. We need to get our bioreceptor onto the surface of our nanoparticle labels. Again, the most common way to do this is through physical absorption, particularly with gold nanoparticles. So the pros here are that this requires no additional functionalization, no reagents, it's inexpensive and relatively straightforward. The con, of course, is that the conditions for each new antibody and antibody nanoparticle pair must be optimized individually. So you have to find an optimal pH, load rate, and buffer composition. Now that being said, because physical absorption is the most common way to go about this with gold nanoparticles, there's a lot of expertise out there in both development groups and manufacturing groups for doing exactly this. There is another option though, and that's covalent binding. And there's many different ways to approach this. Two common ones include carboxyl terminated nanoparticle labels and streptavidin terminated nanoparticle labels. For the carboxyl terminated nanoparticles, those carboxyl groups will react with amines on the antibodies through EDC-NHS coupling. For the streptavidin, that will bind to biotin that's been previously conjugated to our antibody. So there are some advantages to using covalent binding: increased conjugate stability. There tends to be a more standardized approach to conjugation, so there's less variation from one antibody to the next. And ultimately, you can achieve a better accessibility of the bound antibody, which can lead to higher sensitivity and better performance. But of course, it comes at a cost. It comes at a cost of being more expensive and typically a more complex number of conjugation steps. So again, you have to weigh the pros and cons here. If you can achieve the required assay performance with physical absorption, that's a great way to go. You're going to find contract manufacturers and other manufacturing groups that have lots of expertise in this area, so that design transfer can be relatively smooth. But if your assay requires higher sensitivity or another advantage that a covalent binding approach can give you, then that's the way you should go. Now, the last two decision points we're going to talk about here are not so much about the reagents or the chemistries, but more about the format of the test. And these are things that you may not really think about early on during development. They may be things that you're putting off towards the end of development, but you shouldn't. The first one has to do with a dipstick test versus a cassette. So a dipstick test, in the simplest sense, is just a bare strip, or a bare strip with some cover tape on it to protect it. These tests are fairly easy to manufacture, and they're less expensive to manufacture. On the other hand, we have tests that come in a plastic housing known as a cassette. And the cassette tends to make it easier to handle, easier to use the test in the field. But if you're going to use a cassette, you should really be thinking about this early on in development, because this, number one, the cassette geometry should be chosen for manufacturability. You want to make sure your manufacturing partner can easily put the strips into cassette at scale. And you also need to realize that the cassette itself can and will alter the flow of the sample up the strip. And so when you're doing your development, it's important to be testing at each stage using your chosen cassette. The other aspect of a test format that should be considered early on is the readout. In other words, is your test going to be qualitative, that is a visual test, or a quantitative test using a reader? Now, this decision may not really be up to you. You may require a quantitative readout. In other words, you may be required to estimate the concentration of your analyte in the sample. But it's good to keep in mind that a qualitative test, as you'd imagine, is simple to use. It requires no external equipment. And to some extent, it can be easier to achieve specification during manufacturing. Of course, the downside is that it usually only provides a yes or no answer. Quantitative tests, in other words, allow you to predict or estimate the concentration in your sample, but you'll need an external reader. And if your test is going to be quantitative, it's important to begin to test out different readers and use them and qualify them early on, because that reader will be part of your test. So to conclude this first half of the talk, I just want to say again that it's important to develop with scalability in mind. You want to, when possible, to keep the chemistry and design as simple as you can, if you can still reach your performance criteria. You want to watch out for cost and availability of your critical reagents and materials. And you want to think upfront about the format, whether it will be dipstick or cassette, and whether or not it'll be a qualitative or quantitative test. The lateral flow test is only as quick, simple, and inexpensive as you design it to be. To conclude this first part of the talk, I do want to mention some resources that are out there, and you'll find many out there. First off, here at Ethos, we do provide a lateral flow starter kit. And in the second half of this talk, Fred's gonna dive into some of the materials available in this kit and what they're useful for. And really what that kit does is provide you with a sampling of different pads and membranes for development. Ethos also provides 40 nanometer gold that's ideal for lateral flow assays. Our partner company, Bangs Labs, have other nanoparticle labels like europium chelate. And here at Ethos and Bangs, we've been doing lateral flow contract development manufacturing for many years. So with that, I want to pass off to Fred this webinar so he can talk more about the material aspects of development and manufacturing.
Thank you very much, Ryan. Hello, everyone. I'm Frédéric Devien, Product Development Manager in Ahlstrom. And in the second part of this talk, here we are going to see a bit more on details. What are those fiber-based components used in the lateral flow immunoassay? Before jumping in details, I would like to present you briefly Ahlstrom company. Ahlstrom is a leader as a fiber web solution provider for different market and daily application. We have a global presence worldwide with 37 plants and 7,000 employees. In Ahlstrom, we develop, manufacture, and sell fiber-based media to purify and protect for a more sustainable world. We have the ambitions to become the preferred sustainable specialty materials company, supported by strong values like team spirit, accountability, and cares as well. Here is a quick overview of the three product categories proposed by our business unit, which is Lab and Life Science. The first category, laboratory, proposes a lab filter with different size and with also a specific application in air monitoring. Second is the bioprocess, with materials used in the bioreactor or in plasma fractionation process, for example. And finally, more used in diagnostic and care, we have the materials for life science application. Today, the focus will be on the fiber-based components used for rapid test kits, what we call RTK. As Ryan stated earlier, the choice of all raw materials is quite crucial for developing a robust lateral flow immunoassay. To facilitate your access to all components and startup investigation on lateral flow immunoassay, Ethos Biosciences team proposed a starter kit consisting of all solid items. That means backing, cassettes, and membranes involved. Among those, some Ahlstrom products based on fiber materials are in. The manufacturing process and use of this component in RTK are very different of the nitrocellulosic membranes. Visible on the top right corner, you see that materials are made of fibers, and here in the selections for the starter kit, we focus on glass materials grade 8950, 8951, 8964, and also cotton materials grade 222. Whereas all these four grades can be used as a sample pad, for the conjugate pad and a wick pad, it is a bit more discriminant. For the conjugate pad, the porosity and the non-interaction with the antibody is quite crucial to let the conjugate get immobilized and released correctly. So it makes the use of the three grades of glass fibers exclusively reserved for this application. The three types of glass fibers are mainly different by their manufacturing process and also their properties in overall. 8950 is the thinnest one. The wicking rate faster for 8964 and slower for 8950. If we consider the hygroscopic properties of the grade 222, it is the best candidate to get used as the wicking pad and absorbent pad. Or absorbent pad, I would say that that's the same word, wick pad or absorbent pad. Something quite important to consider from the beginning and could have a favorable impact on the manufacturing steps is the fact that glass materials can be used as a sample pad and conjugate pad. And so why not considering those as a monomaterials instead of having two separated pads in the lateral flow immunoassay constructions? If we keep talking about rapid test kit manufacturing stage, as Ryan said, it is coming at the final stage, but we should keep it in mind from the beginning. So different type of format are available, from sheet for lab development to already cut strips with desired dimensions for people assembling manually. For those who have the ambitions to use the real tool equipment, we are able to provide materials in the rolled format. All grades in the starter kit are suitable for lateral luminosity productions with the real tool equipment without any fear of breaks, thanks to a strong mechanical properties which can endure the machine tensions. Other things to point out are dimensions and the tolerance in roll or strip width. For all grades in the starter kit, they are available in the narrow widths and very low tolerances, which is not the case for all grades on the market. Finally, especially for roll format, the conventional roll length is 100 meters, but longer or shorter materials can be dimensioned to specific apparatus or for limiting the handling and saving time at the end. In the starter kit presented earlier, we identified some grades to start working and developing with. However, Ahlstrom has other materials I would like to present you now. As previously stated, Ahlstrom provide to its customers sample pad, conjugate pad, and absorbent pad or weak pad. Here is the overview of our complete portfolio. As you can see, media are made of different fiber nature, like natural, artificial, or synthetic fibers. Some are even biodegradable and identify here with the green leaf. Ahlstrom has a wide range of thickness and absorption capacity materialized here by the WAC, water absorption capacity. The information on the wicking rate give a rough pictures of the flow velocity and make customers able to pick also grade based on this according to the needs in quick flow or a slow flow. Let me going a bit deeper on each pad categories. First, the sample pad. Ahlstrom offers materials able to drive the flow and even filter out components like cells or particles, which could not flow along the membrane. Based on the knowledge of our media and also the customer's interaction, we build up this table guiding customers with best materials to test in function of the matrices used. Behind the various number of fibrous natures, the differences are also in the thickness and porosity. Low porosity materials for those requiring filtration like blood, raw milk, and other materials with any particles. As far as the conjugate pad is concerned, all are quite open to ensure the release of all type of label conjugated antibodies. Once again here, different natural fiber are used to let the choice to the customers finding the proper conjugate pad, which work the best in its specific applications. Depends on the type of antibody, buffer, analytes, labels, and others. The range of thickness for this pads is more narrow. Glass and synthetics are quite famous. Less known are blend or even PLA, like the grade 6618. Both are more sustainable than glass and synthetic materials. Our materials do not have the same homogeneity of distribution fibers. Roughly, we could group them in two families. Basically, on the left, the heterogeneous one, and on the right, the best homogeneous materials. Squares in these pictures here materialized the size of a conjugate pad. So you can see that even fibers density will drive to even immobilization in release of the conjugated antibody, better from pad to another pad. So it lets suggest that homogeneous conjugate pad will be more suitable for quantitative assay development. This case study, based on the ACG detections, illustrates the previous remarks on the homogeneity. 89 grades are glass fibers, and here 66 grades are synthetics. The 6613 and 8964 are considered as less homogeneous than 8980 and 6614. Whatever the nature of the fibers, we observe the same trends with lower CV of the pregnancy test for homogeneous conjugate pad used. That makes us confident to promote more heterogeneous media for qualitative assay development and homogeneous one for quantitative one. Finally, as far as the absorbent pad is considered, finding the best compromise, mainly in case of the cassette design, to make sure that it fits the cassette and absorb enough is the key. As another features to have in mind once optimizing the test, it could be the absorption kinetics. That's inform how fast materials absorb. It can help for quick clearance and improving again the performance in overall. Thanks again for your attendance. If you have any questions, please feel free to reach out to Ryan or myself. Thanks.